Well, feels good. Good morning, everyone. I'm Wenqing Shao. I am a PhD student from Telecom Paris Tech. And today I'm going to talk to you something about the traffic engineering interdomain context, and it's measurement-based one. And it's a piece of collective work, and I'm just speaking on behalf of the team. And we work closely with our industrial partner, Border 6, who has an implementation of this measurement-based interdomain traffic engineering system called NSI. And here's the control, I guess. Oh, snow. Is this purple one? Yeah, it's rolling. Yeah, good. Thank you. Yeah. And today, and the plan is that we are going to show what do we mean by this measurement-based mechanism and why we could possibly wanting it. What are the challenges in general in building such a system? And then I will show you a concrete case, a problem, a challenge that we have, a scalability one in building such a system. So let's begin with BGP 101. You're not liking it? Yeah, but the script is that I'll just continue. The BGP is a distant vector routing protocol, and like routing protocol of other flavors like OSPF, it doesn't take into account the performance metrics in doing decision, right? And possibly not the worst part of it. But the point is that when you are performing traffic engineering within a network, as long as there's no congestion, the delay is quite predictable. But when it comes to the interdomain context, one has actually to measure to know what are actually delay of a certain AS paths, because there are so many factors beyond our control. So the idea is that, okay, we are going to choose the best BGP next hop based on measurements, right? The smallest delay, for example, we are just kind of choosing it. Sounds very easy and straightforward. And now I can read from some of your faces saying, okay, so what, right? And I perfectly understand just looking at this list of publications and when they are publicated. And in this ever-evolving world of technology, any idea that is half of my age could be anything but sexy. But the point I'm bringing up this stuff today is that actually it is not a trivial quest. And more efforts are actually needed to turn this idea into a well-working system. And talking about efforts and challenges, just think about that. We are going to measure the delay toward all possible destination networks via all possible transit providers. And there could be around 600K of them. And how we could really possibly do it. And I'm going to demystify some of the building blocks, major building blocks of such a kind of system. And they are illustrated on the bottom of this architecture graph. You don't have to capture all of them just right now. I will just walk you through one by one. And at the beginning of the pipeline, we collect traffic statistics from NetFlow, SFlow. It's a quite standard and common operation, and many softwares, open source or commercial ones, provide this kind of functionalities, and some of them also offer very beautiful graphic interfaces showing you the distribution of traffic volume over, for example, router interfaces, destination countries, or application types, whatever. You surely know that. But our usage of these statistics a little bit different. We aim at kind of finding out a subset of prefixes that are important, so we can focus the measurements and the optimizations on them. And we will come back to this part later in detail. And once the prefixes of importance are selected, we are going to measure them, right? And first of all, we are going to find IP addresses that is responding to active measurements. And one common trick in topology measurement is to look into traffic traces or DNS request logs to finding IP addresses hosting open services. So we can ping with TCP sync or whatever, so we can measure delay and then loss toward them. And one uncommon operation involved here is that we are going to steer the measurement traffic via all possible BGP next hops. And this can be done with a variety of ways. We can use some source-based routing mechanism, like kind of segment routing, or in more flexible SDN flavors. And it's just doable stuff. And finally, it's a route decision. Is how we choose the best BGP next hop based on measurements. And there could be multiple possible objectives, and the realization of which is totally depends on the user's need. For example, there could be users that are more performance sensitive. For example, like kind of online bidding system for advertisements, and others are more cost sensitive. And I'll just kind of walk you through some of the classic optimization cases, so to have a concrete idea. And here, the first, cost. First, we'll review quickly how we calculate the transit cost. And we know that there are two parameters involved, the 95th percentile of bandwidth, and sometimes, and many oftentimes, the committed data rate, the CDR rate. As long as the 95th percentile rate doesn't exceed the CDR rate, possibly we have a flat rate. It's a fixed cost, no matter how much you use, right? And in this case, we have incentive to maximize the utilization and push it as close as to the CDR rate. And once we exceed the CDR rate, extra fee can be generated, and it's linear to the exceeded part of the bandwidth. And now just let's go back to the graph. What does it say? Before the optimization has activated, here first of all, we have three transits. Transit 1, 2, 3. 1 is the cheapest one, actually. The transit 2 is the most costly. And before the optimization has begun, we actually consume more transit 2 than transit 1, and both of them already exceed the CDR rate. And on the same time, we have transit 3, which is largely unused. And its 95th percentile bandwidth is far below its CDR rate. So what happened after the optimization began? We have an obvious increase in the usage of transit 1 and transit 3, and a decrease in transit 2, which prevents an even higher 95th percentile bandwidth usage on transit 2, and eventually a smaller bill. And on transit 3, we just kind of literally push it as closest to the CDR rate. And you might say, okay, that is doable even with playing with local preferences. We are going to set a higher value for transit with low costs. But so why the triple measuring all these stuffs? Because there are moments that performance factors come into play, right? And rule number 1, if possible, don't let instant bandwidth exceed the CDR rate, because there could be packet losses, whatever. Not interesting stuff. But the story doesn't stop here, because when you don't exceed the CDR rate, there could still be packet losses somewhere in the middle of the internet. And here is a graph showing the packet loss rate for two transit providers, transit 1 and 2. And we can see that naturally, BGP just chooses transit 1. So it has kind of, which has this phenomenal diurnal pattern of packet loss, indicating a consistent congestion, right? And while we don't really see transit 2 here on this graph, because it has literally 0 packet loss, that is to say, the natural decision of BGP is suboptimal. And this kind of observation just cannot be made if we don't perform continuous measurement and draw the conclusion. But once noticed, the solution is quite simple. Just switch to transit. Done. Much better. And even when there's no obvious packet loss, the traffic can still be sent out on a slow path. And here's an example. Between transit 1 and transit 2, the difference is about 70 milliseconds. It's quite a long time in networking. And again, this kind of difference can be seen if we don't perform continuous measurement and analysis, and to be sure that there are such differences. And once noticed, we can optimize them. And all these three cases are also the reasons why we might be wanting this kind of measurement-based traffic engineering system. And because these needs won't be reviewed if we don't measure. And that is so far for the outbound part, how to choose the BGP next hop in sending out the traffic. But So what about inbound part? The inbound traffic engineering with BGP is known to be lack of fine-grained and effective measures. There is pending stuff and BGP communities, but it depends on your transit provider. The support is different. And so we are proposing this route preference protocol, which allows the traffic receiving AS to communicate to traffic southing AS its preference of ingress point. It's sort of like Lisp without encapsulation. I don't know if you are familiar with Lisp, the locator identifier separation protocol. If you don't, it's okay. Just think about MAD, multi-exit discriminator in BGP. It works sort of like MAD with remote yet targeted influence, right? The idea is based on the observation that if the traffic sourcing AS changes its next hop of going out, sending the traffic, the chances are that the traffic receiving AS is going to see the traffic coming in a different ingress point. So if the traffic sourcing AS is just doing some tie breaking, why not do a little favor to the traffic destination AS? Could be a better world. And this can be useful in the case that the IOs or content providers haven't yet paired with each other, for example. And I would also like to make two quick remarks. In what this kind of communication takes place correctly, we are actually two controllers speaking a common tongue needed in both traffic sourcing and traffic destination ASs. And for that purpose, we are working on an open source implementation of the controller and also trying to bring up some efforts in the normalization, IETF normalization stuff. And so far for the building blocks of the system, how we do this stuff. And now we are jumping into the scalability question. As I have mentioned earlier, the purpose of collecting traffic volume studies is to allow us to select a subset of prefix of volume importance. And the reason why we are doing so is that we just can't afford monitoring all these 600K BGP prefix. And there's no need in doing so, because we know that a large part of internet traffic concentrates on a small part of prefix. And don't stare too hard into this graph, you'll get dizzy. Just kind of scientific, scientific decoration. The main message is that for certain networks, the top prefixes, some top prefixes can stand up to 10% of the total traffic volume, which is quite impressive. And for some networks in whole, with top 1,000 prefix over the week, it covers actually 90% of total traffic. By optimizing for these destination prefix, we control and we optimize a large part of total volume, which is great and saves a lot of efforts. But the point is that we can't just simply select a static set of prefix and assume that they are going to represent a dominant amount of volume all the time, because it's not the case. Traffic volume changes. And don't stare too hard into the graph. So we have to predict for future moments. What are the prefix going to be important? And then repeat this kind of prediction from time to time. Talking about prediction, we are good at it since we do network dimensioning. It involves a lot of algorithms and doing these predictions. And the point is that these mathematical models, good, beautiful mathematical models, are just so complicated when we have some tens active prefix to predict. So our quest is to predictively select BGP prefix, destination prefixes that stand for a large portion of traffic, but with a very, very simple method that scales out, right? And we are doing this for the purpose of saving resources that we use in measurement and optimization. And we also know at the same time, if we arrive at solving this problem, it also saves resources on data plane as well. Just imagine previously we have a full BGP routing table on the routers, and now we have one optimizer route for each selected prefix, and finally a default one for the rest. This transition allows us to use these cheaper DC switches, which don't have a huge bunch of flow tables entries or SDN switches, instead of these expensive edge routers. And at this point, you might be thinking, okay, that sounds weirdly similar to those forwarding table caching or prediction work, right? And actually, we are not the only one who thinking that way. So just a quick look at the forwarding and table caching and prediction problem. It aims at selecting a popular subset of routes and install them on the forwarding table, the TCAM. And this kind of functionality is widely supported on switches and the routers 20 years ago, since back then the TCAM was expensive. And more recently, with the rise of SDN concepts, whatever, and network runners are tempted by these low-cost open flow switch fabrics, right? But the point is that they are not known to have large flow spaces, around 2,000 if you are lucky and rich. And so David Barroso of Spotify very intelligently brought back this forwarding table caching or prediction idea back into the SDN context, so we can use these cheaper routers even at the edge of the network. And so what's the difference between the fit caching or prediction work and our perfect selection work? Basically, it is a difference of time. With perfect selection, we are actually working on a longer interval because we have to look for probes within destination networks. We have to find out which ones are more reliable so we can base our decisions on. And we have to learn for long-term traffic patterns for bursty traffics. And with all that, we have the preference for lower perfect train, for lower perfect train because they are very complicated and time-consuming operations. And that is more than that. There is something related to traffic dynamism. And here's again a very dizzy graph. Don't stare too much into it. And I'll just kind of explain what it does. This graph comes from a very well-written and insightful Infocom paper telling that on short time scales, 5 minutes or so, on flow level, 5 tuple flows, the bandwidth of these flows are actually very versatile. There's no evident correlation between the bandwidth and the stability. While the fit caching and prediction guys just assume that there's a positive correlation between popularity and the stability. And in that case, a natural question arises. So what's the case in perfect selection? What happens to traffic aggregated by BGP prefix on longer interval, say 1 hour? And that is what we found. Again, an overloaded graph. Don't stare too hard. Focus on lines. Squint if you are appreciating and impressionist painting. Could be better. And what it's saying is basically that this graph tells the relationship between volume importance and the predictivity of these prefixes. And we have this tendency, that decreasing tendency as we move to the right side of the graph, where prefix of large volume share resides. While on the y-axis, it is the coefficient of variation of all volumes of this stuff. Basically, it describes stability and predictability. Smaller the value, more stable. Our volume is centered around its mean volume. That is to say, larger prefix are more easily to predict, which is definitely a good news for us. But just note that there are also exceptions. See the green line at the far right end. It is caused by one single prefix that the local network rarely sends traffic to it, but in most of the time, don't send traffic to it. But on very rare occasions, a huge amount of traffic is sent in a short duration. It is normally caused by data center synchronization or hotspotting SDNs, and that is going to affect the volume coverage of our traffic prediction stuff. So, given these observations, we can actually opt for a very, very simple method, selecting these important prefixes, as simple as moving coverage, right? And that is what we found. This box plot shows the volume coverage of this moving average model, and it compared to the gray model, the GM11, previously used in forwarding table predicting. It is reported to be better than LFU and LRU. And we can see that with moving average, much simpler method, have a much better coverage compared to gray model. And for this specific network, with 10% of active BGP prefix, we are able to cover 90% of total outgoing traffic. And a quick recap, we've seen together the building blocks of a very old, unsexy scenario of traffic engineering, which happens to be measurement-based. If we give it a close look and a second thought, we can actually find there are quite interesting problems remains. And we just quickly dived into one of them, a scalability one, how we select prefix of important volumes. And by leveraging the traffic volume characters, we can use very simple method in doing so. And of course, there are many more challenges. And one of them is, again, concerning measurement and how to select probes with reliable measurements. As I have mentioned, we might cover multiple end hosts that are responding to our active measurements, and they are all measuring the same AS path, but yet they are different in IP levels, for example. And natural question to ask is that why they are different, how they are different, and where does these differences take place, and how, by understanding these questions, is going to help us selecting the best probes to use, so that we don't just accidentally switch 40 gigabytes from one transit provider to another because some accidental or stupid lot of oscillations of RTT that we don't actually control, or we don't actually possibly can optimize by switching the AS paths, for example. And by using some clustering techniques, we are able to group these RTT time series into two groups. And they are very different, as we can see. And in the paper just kind of earlier, we explained why this is happening, how we can possibly identify these problems and group them into two different groups. And the message of this presentation, which goes beyond the context where the context of this presentation, the traffic engineering stuff, is that in the networking of nowadays, we have to measure to see what is happening there, instead of just sitting on what we have and be happy about that. And it's with analysis, we can find network events of true importance and understanding the root causes. And finally, with automation based on observation instead of intuition, we can finally free network engineers from their daily routines. And finally, there are some references, groups in different categories for those curious minds. Some of them are quite aged, but doesn't mean that the solutions they bring forth, or the questions they are working on are not interesting. Just think about the flip caching one. If we put it in the right place, in the SDN context, it's going to serve us well, right? And at this point, I'm happy to take questions, and also I'm happy to take short speech, discussing questions, sharing your opinions on this. What do you think about this scenario and your experience on measurement and traffic engineering? Thank you very much. Any questions? So if you don't have specific questions, just so you know that the engineer who literally coded the system is also sitting down among you. If you have specific questions, don't hesitate. He's willing to take it. Okay, so thank you very much.